Hello everyone. In the notes today we're looking at showing two triangles are congruent, but in this case the triangles are going to be right triangles. So we have a little bit of a different setup. We're going to talk about what a perpendicular bisector is, how they form right triangles, and then talk about the perpendicular bisector theorem, and then use that as a way to work towards our final pattern that we've been studying about showing triangles are congruent. So first I'm going to do a little bit of a construction here to create a perpendicular bisector. So given this segment from A to B, I used my compass and I drew these two semicircles. These are arcs, and they came out very lightly because the pencil is very, you can barely see that. The pencil is very hard lead there, but we're trying to draw two arcs. One is a semicircle around center point A, and then the other is around center point B, like this. And what we're really looking for are where those two arcs intersect each other. So we have a point of intersection here and here. And so those two are going to then guide our straight edge to create a vertical segment like this. This is going to be a perpendicular bisector. And so what we have now is that this vertical line is perpendicular to the original, and it is a bisector, so we put tick marks on either side like so. So that's how we've created a perpendicular bisector in the past. What we're doing is we're going a little bit further to create some triangles here, and let's pretend that we are going to place a point C, and it could be anywhere, it doesn't have to be this point of intersection. But if we place a point on the perpendicular bisector, and here we're calling it point C, let's now create the third side of our triangle by connecting point C back to the endpoints of the original segment. So you have a triangle on the right and another on the left. The question is, are they congruent triangles? We're going to be doing more work with that in just a moment. But if you think about the fact that we have a pair of right angles, we know right angles are congruent. We have a pair of congruent sides because this is a midpoint. Then this side happens to be shared between the two triangles, and it will also be congruent. So we could say, yes, we do have congruent triangles by reason of side, angle, side. So if the two triangles are congruent, then that means they're exactly the same. And what we want to do is we want to just take some data. We'll take some measurements here. How long is this slanted side? How long is this hypotenuse, right? Because if this is a right angle, then that means this side is not just any side, it's a hypotenuse. And so if I use my ruler here and just take some quick measurements, and it looks like we have about 3.6 centimeters. My measurements might be a little bit off if I drew my construction carelessly. So it's possible that our measurements could turn out to be a little bit different here. But in general, if we know that the two triangles are congruent, then that means all of the corresponding parts have to be congruent. That means this hypotenuse would have to be congruent with that hypotenuse. So we should be able to conclude that our two slanted sides are congruent to each other. And what that does is it leads us into the perpendicular bisector theorem. So I'll skip over this fifth part here and jump down to the bottom. So here it says perpendicular bisector theorem. So here we have in a plane. That's talking about a two-dimensional object. All right, so in a two-dimensional space, if a point, that's this point here, C, if a point is on the perpendicular bisector, so here's the perpendicular bisector, how do we know that? Well, there's a right angle, so it has to be perpendicular to the base. And here's your tick mark, so that has to be a bisector of the base. So yes, if a point is on the perpendicular bisector of a segment, then it, meaning this point is equidistant. Equidistant means it is equally far from these two endpoints. It is equally distant. So we can conclude that the length from A to C is equal to the length from C to B. And that's because these triangles are going to be congruent. And we're going to show that in just a moment. So this is what we were just talking about. If this line CP is the perpendicular bisector of the base AB, then that means the length from C to A is equal to the length from C to B. That's the perpendicular bisector theorem. Now, we didn't really prove it here. This was just a demonstration, and now we want to prove it, and that's what we'll do on the next page. So, example 1, it says complete the following proof. Notice that we have essentially the same diagram. CP is the perpendicular bisector of segment AB. So given that we have a perpendicular bisector, let's prove that the length from C to A equals the length from C to B. All right. So we have a lot of information here if we have a perpendicular bisector, because we have to talk about what it means for things to be perpendicular, and then we also have to talk about what it means for there to be a bisector on a segment. Okay? And so what we're doing here is we are taking this, and we have both pieces of information, the fact that we have a perpendicular pair of segments and that we have a bisector going on. That's really two ideas in one statement. We're putting both of those ideas on reason 1, so that is given, but now we're going to split this up a little bit and say, okay, what do we know about this perpendicular segment? Well, there it is. We're just naming it. So that is really going to this first part. And what is this bisector doing? This bisector is creating a midpoint. And so this is really what's changing. This first part stays the same. Here it says they're perpendicular. Here it still says they're perpendicular. That's just really kind of bringing these two names together in one place. Okay. If I have a bisector, then it creates a midpoint. That's my if then that I want. So if there is a bisector, then midpoint. So what we're really saying is that if there is a bisector, then it creates a midpoint on the segment. So if I have a midpoint, then that means that the pieces of the segment on either side of the midpoint are going to be congruent. And it's already marked here with tick marks. If it's marked, we have to name it. So now we're continuing this idea of, okay, what is the midpoint doing? It's creating these two congruent segments. So we have a segment AP is congruent with segment BP. And that's our definition of a midpoint. If a point is a midpoint, then it divides a segment into two congruent segments. So now we're coming back up to that first piece of information, which was about the perpendicular. What do the perpendicular lines do? They form right angles. So if perpendicular lines, then there are right angles. Remember, you have to name the angles. So this is angle CPB. We also have another one on the other side. This is angle CPA. All right, so angle CPB is, I almost wrote down the next line by accident. Again, we're just naming them here because these are the angles that are formed by the perpendicular line. So angle CPB and angle CPA are right angles. So notice we're not saying they are congruent yet because perpendicular segments form right angles. Now we can say, what do we know about the right angles? Now the right angles are going to be congruent. So if you take a look at what we have so far, we have one pair of congruent parts, two pairs of congruent parts. We're trying to show the triangles are congruent here, so we need to look for a third pair. And there's your hint, reflexive property of congruency, so that's the shared segment from C to P. So segment CP is congruent with itself. And now we have three pairs of congruent parts. So now we can show that the triangles are congruent. So remember, our goal here is to not just focus on the triangles, but on these slanted sides of the triangles. We want to show that segment CA is going to be equal in length to segment CB. So we have to first of all show that the triangles are congruent, then we can talk about a very specific pair of parts on those triangles. Normally our proofs have been essentially just showing the triangles are congruent, but now we're going to be going a little bit farther and looking at specific parts of those congruent triangles. So what's our reason? Look at the markings on the diagram. Here's the shared side, that's our reflexive property. So looking at one of those triangles, you see that we have two sides that are marked and one angle between them. So this is a side angle side pattern. Alright, so now we know the triangles are congruent. So if the triangles are congruent, then that means every pair of corresponding parts will have to be congruent too, even the parts we haven't used yet in our proofs so far. Even these angles, like angle A and angle B, they would have to be congruent because they sit on a pair of congruent triangles. Well, we're not focusing on the angles, we're focusing on these slanted sides. So let's look at segment CA and segment CB. Are they going to be congruent? Of course they are, because they're sitting on two triangles that we've just shown to be congruent. But we have to name them. So segment CA is congruent with segment CB. So here's a new if-then that we have not seen before. This is going to come up more in the days to come. And here's the if-then form of that. If two triangles are congruent, right? The if part always describes what came before. We just showed that two triangles are congruent. So if that's true, then corresponding parts are congruent. There are other pairs of corresponding parts. Notice that we're not being so specific to say corresponding segments or corresponding angles. We're just calling them corresponding parts, and they must be congruent. Why? Because they are on two triangles that we just showed to be congruent. This specific proof is asking us to go one step farther and say show that they are equal in length. So that's our final transition here. If we have congruent segments, then they have equal lengths. So again, this is your definition of congruency, and you can use that title if you prefer. So what we've done here is we've started with a perpendicular bisector, and we haven't really focused on the fact that the triangles are right triangles, but we've focused on the fact that we have a perpendicular bisector, and now that you have a perpendicular bisector, we know these slanted sides are going to be congruent. That's the perpendicular bisector theorem that we just proved. And now we take a closer look and say, hey, wait a minute, these happen to be right triangles, and they're hypotenuses. So that means we now have another way. This leads us into our final way to determine that triangles are congruent. And that's kind of what this is saying here. Even though we proved that these triangles are congruent by side angle side, there's another theorem that proves the triangles are congruent, but this only works for right triangles. So if you have a perpendicular bisector, you have a right angle, which means you actually have a right triangle. So if you have a right triangle, you have a hypotenuse, and we just show that the hypotenuses are going to be congruent. So what that means is that we have a right angle, so we have a right triangle. Because we have a bisector, we know these segments are going to be congruent. And we just proved up here that the hypotenuses are going to be congruent. And so this is what we call the HL pattern. Because in a right triangle, the side that touches the right angle is a leg, so this L stands for leg. And the side that does not touch the right angle, the side opposite the right angle, is the hypotenuse. So your book is going to call this the HL pattern. However, I'm going to add one other letter in here, and because we have a right triangle, I'm going to call this the RHL pattern. So I'll ask you to do the same. RHL instead of just HL. We are being a bit redundant here because a hypotenuse only exists on a right triangle, so we're sort of saying right triangle and a right triangle with hypotenuse. But I like the three-letter combination because it fits all the other three-letter patterns that we've been learning about, like side, 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 or side, angle, side. Also, when you do your proof, you have to check to make sure that you have a right triangle. You actually have to have a line in your proof that says, this is a right triangle. Then you identify the hypotenuse and the legs as well. So if the hypotenuse and a leg of a right triangle are congruent to the hypotenuse and a leg of a second triangle, then the two triangles are congruent. So notice also in this case we have only two pairs of congruent parts, even though we really have three with that right angle. When we write our proof, we're only looking for two pairs of congruent parts, a hypotenuse and a leg, because the third pair we actually focus on them being right triangles, not just congruent angles. So we're going to do that now using this new pattern in this final example of this proof. So here we are given that segment YW is perpendicular to XZ, so right angles, and segment XY is congruent to ZY, so that's our starting position. Alright, so let's identify this. Here's line 1, segment YW is perpendicular to segment XZ. I'll use the same line. Segment XY is congruent to segment ZY, and of course that's given. Now I've already marked the right angles here, but perpendicular lines always form right angles, so we've marked it, we have to name it. So here on line 2, we're just declaring that these angles are right angles. So angle XWY and angle ZWY are right angles. And here's our if-then statement. If perpendicular lines, then right angles. So now that we know we have right angles, what do you think comes next about those right angles? Normally, we would say that they are congruent, but we're not going to this time. Here's an example for contrast. Look at the previous proof. Here, we said these angles are right angles, and there they are. Clearly, we have right angles. We then went on to say that we now have congruent angles, because we know that all those right angles will be congruent to each other. But the reason why we did it here is because it led us to a very specific pattern. It led us to a side angle side pattern. If we were to go as a next line and say that the angles are congruent, and let's pretend for a moment we did that, so I'm using my scrap paper here. Let's pretend that we said angle XWY is congruent with angle ZWY. There's nothing wrong about that. It is a correct statement. They are congruent to each other. We just can't use this. And the reason why we cannot use this is because of the placement of the markings. When we get all of the parts marked, and here's our shared side, so we're going to have that marked here in just a moment, this is none of the patterns that we've studied. In other words, we cannot use a side-side angle or if you want to go backwards, angle side side pattern, that doesn't exist. This does not guarantee triangles are congruent. We cannot use the side side angle, or angle side side. Instead, we have to find a right triangle so that we can use an RHL pattern. So because I have right angles, I am not going to say they are congruent. Instead, I'm going to say I have right triangles. So triangle XWY and triangle ZWY are right triangles. Our if-then statement is, if triangles have a right angle, then they are right triangles. So this line happens to be the R part of the RHL pattern. And so when we took a look at this given information here saying that segment XY was congruent with ZY, that's the hypotenuse right there. So that's the H. So we have the R, we have the H. We need one more pattern, or excuse me, we need one more pair of corresponding parts, and that'll be the leg. That'll be the shared side. So from W to Y, that's the leg of the right triangle. So we can say segment WY is congruent to itself. That's our reflexive property of congruency. And notice how this is different from the proofs we've done in the past. In the past, we have always looked for 3 pairs of congruent parts, right? And I've numbered them each time. There's the first pair, there's the second pair, there's the third pair. We see that on the previous example, 1, 2, 3. Here, it's only 2 pairs of parts, because what would have been the third pair is not a third pair of congruent parts, but instead an identification that we have right triangles. Again, why do we have to do this? Because if we tried to say that our right angles are congruent, it would lead us to a pattern that does not exist. We simply cannot use a side-side angle, or an angle-side-side pattern. It will never guarantee that the triangles are congruent. So remember, there are some patterns that work, but not every combination of angles inside will show triangles are congruent. Only certain patterns, and we have to know what those patterns are. Here's our conclusion. The triangles are congruent. And this is our RHL.